Okay, so today we're going to get started with just a review of radicals, right? Square roots, cube roots, fourth roots, things like that. This is from the appendix of our textbook. It's called section A1. So if you want to look in a textbook, whether online or in one from the room, you could do that. And really what we're going to do is just define what an nth root is. Right? Nth meaning it could be a, if it's a 2, it's a square root. We don't say second root, or a 3, it's a cube root, or a 4 is a fourth root, or a fifth root. Really all that means is, and for today, this is all going to be with real numbers. I know that you've worked with the imaginary unit. You've talked about taking square roots and negatives back in Algebra 2, which is great. We're not going to have to worry about that today, though. We're just going to think about real numbers, right? So we're just keeping it real. So the real nth root of a real number, what happens is we'll see later on in the year, is when you do have nth roots, there's usually more than one, right? When you start to deal with imaginaries and complex numbers. So what we have here, and with any good definition, you're going to be given some pieces of information in the beginning. So here, let n be an integer greater than 1. Integer means it's going to be a positive whole number, right? Because it's greater than 1, so it's 1. So it's 2, 3, 4, 5, etc. And let a and b be real numbers. It could be any real number. It could be a fraction, it could be a decimal, whatever. But it doesn't have any imaginary unit to it. And our definition is that if the number b, the real number b raised to the nth power is equal to a, then we say that b is an nth root of a. So what that tells us is if you have, let's look at a couple of numbers that we know. So if we take 5 and cube it, let's not cube it, let's square it, we get 25, correct? So we'd say that 5 is a square root of 25, is what that means there. Oh, thank you. Okay, great. And then, but also here, we have that negative 5 squared is also 25, right? So they're both square roots of 25. 5 is a square root of 25. Negative is a square root of 25. Because really, you don't know if you square which one you're going to go ahead and get there. Or, well, you know what you're going to get, but you don't know which one you actually squared to get it. So really, kind of the big thing is here, since they're both square roots of 25, we kind of differentiate. The one that has the same sign as 25, 25 is a positive number, right? So we'd say 5 is what's called the principal nth root. That's all. That's all this was all about. All that writing was just that. The one that shares the same sign and is also a real number, we'll call that the principal root. The other would be the negative root. A lot of times you'd call it, but we don't run across it a whole lot. Okay? So just some, so just to make sure here, let me put a few up here and just make sure that we should be able to do these by hand, the ones that are possible. Is what is the principal square root of 36, right? We'd use the radical symbol to indicate that. What's the square root of 36? Or what is the cube root of 27 over 8? Or what is the cube root of negative 27 over 8? And then what is the fourth root of negative 625? So if you want to take a second, go ahead and think about those, and we'll take a look at what those are. Okay, so as we look at this first example, we're just asking to find the principal nth root, or so here. We have the square root of 36. We all knew that was 6, right? Now, you could also say that negative 6 is a square root of 36, but when it's written like this, we're assuming that it just wants the principal, right? You're assuming it just wants the principal. If it wants the negative one, they'd have to put a negative out in front of the square root to tell you that. Now, if the negative was under the square root, there's no real answer, right? There is no real number that you can square and get negative 36. So that would be 6. Here, the next one, we have the cube root of 27 over 8. Whenever you do get a fraction, it's nice to be able to see here in our properties, you can break it into 2 cube roots. You could think of this as the cube root of 27 over the cube root of 8. Well, we know the cube root of 27 is going to be 3, correct? 3 times 3 times 3, and hopefully you know the cube roots, like at least up to, I don't know, maybe 125, So that would be 3. Then on bottom, the cube root of 8, that would be 2. Notice that 27/8 is positive. 3/2 is also positive. Right, if you needed to check that, you can say, well, what's 3/2 cubed? And that would give you 27/8. So that seems like we did well there. The next one we have is the cube root of negative 27/8. Well, you could kind of, on a cube root, I don't know if you know this, but a cube root, if the, what would be this? The argument, the piece inside there, I think there's a better name for it here. The radicand is the part underneath. I usually just call it the argument, but the thing underneath there. But if it's negative and it's a cube root, then your cube root's going to be negative also, right? Because a negative times a negative times a negative will always give us a negative. Unlike an even root or an even power where the negatives will cancel. So here, very similarly, but we're going to get negative 3/2, right? This will be the principal root, will be negative 3/2 because it has the same side as the argument or the radicand, the thing under the radical. And then, did I really put the nth root? That was kind of silly. Can't do it if it's just an n. It was supposed to be a 4. It's supposed to be a dry erase board too. There we go. So 4. Well, sorry, that was kind of an impossible question. But now it's the 4th root of 625. Do you know that 5 to the 4th power is 625? Kind of a fun fact, but it is. But it's a 4th root, so you're not ever going to get a negative number, are you? Because when you do 4 negatives together, they're all going to cancel. You're always going to get a positive. So here we'd say that there's no real solution. And what that means is, it's kind of a weird mathy thing to say, but it means that there's no set of solution for a real number, right? Doesn't mean there is a solution, but you have to use what complex or imaginary numbers, which are non-real. So we're just trying to stay within the real numbers now. Any questions there with those? So that's if you see principal square root. It's not intended to scare you. And like in this case, you don't really worry about the -6. If they want you to, they'll do here. Now, if they said that x squared equals 36, then you'd have to consider the 6 and the -6, the principal and the negative root. All right. Here are all the bunch of properties of radicals. I put these up here to give you a chance to write these down. Again, like any good definition, let u and v, and you notice my u's tend to have little legs on them, and my v's tend to not be very pointy. That's why you got to find a way to make your letters where you can read them. So let u and v be real numbers. Again, no imaginary unit. M and n are positive integers greater than 1. So again, we know integers are the counting numbers, right? Positives and negatives, and if they're positive, greater than 1, that would be 2, 3, 4, 5, 6, etc. What we're going to do today is we're going to manipulate and simplify radicals, basically. Right? That's what we're practicing here. It's not really learning names, but we're going to actually do these. And these 6 properties will be very helpful. Here, the first one is kind of think of it as a product property. If you have the nth root of a product, right, that it's just the nth root of the first term times the nth root of the second term. That's really the idea behind how we simplify radicals, right, as we do that. Here we get the same thing for division. If you have a quotient, it's kind of what we did here on these 2 examples, right? You kind of look at it at the top, look at the bottom separately. It says if you have a fraction under a root, you can take the root of the top and the root of the bottom. Or you can also, it's an equal sign, you can go this way as well. Right? These are just different comparable forms. Kind of weird looking. I don't know if I'd ever seen it written this way, but it says if you have the mth root of the nth root of u, that it just becomes the product, whatever the 2 indices were. So the m and the n, you just multiply them together. That's going to be your new index on the root. Once we start to talk about rational exponents, I think that makes a lot more sense. But that, a quick example of that is if you had, the cube root of the square root of x, that would be the 6th root of x, right? Because again, we know that if there's just a radical, there's really a 2 there. We don't write it. 3 times 2 is 6. Kind of different looking. Could come in handy. Here we have, why would I put that there and then? Huh. That's kind of weird. Okay. Here, normally is the case if you take the nth root of the nth power, right? They cancel each other out. You just get the argument inside. And then yeah, this is kind of, I'm sorry, this is kind of contradictory because 6 is the same property, is why I'm kind of getting a pause here. Right? Did you guys see it? That's this, well, I guess it's not because it's on the outside. That's the difference here. Okay, so here you're taking the nth root and then you're taking the nth power. This will always end up giving you a positive u. That is, or whatever u is. Here, it just says that if you take a power of the radicand or the argument, you also could have taken the root first and then done the power. You have the option, right? You can either root first, then power, or whatever. An example of where that would come in handy would be if you had, say, the 4th root of 16 to the 5th power. We're working this out by hand. I don't want to do 16 to the 5th power, ever, right? That seems like a lot of work. Okay, but this property tells us we could write it as the 4th root of 16 to the 5th power. We know what the 4th root of 16 is? Just 2. 2 times 2 times 2 times 2. So that'd be 2 to the 5th, which would just be 32. Okay, so a lot of times just by rearranging things, it'll help us with this. Here, kind of a weird one. I probably won't get super picky about this, but some of your...
Excuse me for the interruption. Staff, we have a number of...
Teacher for taking attendance. Good stuff. All right. Here's a little bit of a weird one. This is going to come up in some of the homework tonight when you're checking it. You're going to see these absolute values popping up. And it seems really strange. It's something we need to be aware of, but it's very easy to forget, and I understand that if you do, we'll kind of work with it and try to catch it, but that's where they're coming from. So if you tend to miss them, don't beat yourself up. But what this is saying here is if we take the nth root of u to the nth power, okay, what happens here is u could be any real number, right? It could be a positive or a negative. Okay, so what will happen here is, for example, if you had, I don't know, the square root of -6 squared. Okay. So if we work that out, the first thing we do is we square the -6, correct? So it would be 36. And then we take the square root, and the square root of 36 is +6. So what it's saying here is this property is trying to tell you that you can just drop the symbols, the square root and the squared, but actually the number here changed, correct? So it's saying because we're squaring first, then square rooting, we don't know what the original sign was. It could have been positive, it could have been negative. As soon as we took it to an even power, we lost that information. So that's why we would put an absolute value bar there. So saying the answer is the absolute value of 6. We don't know exactly what the original thing was, but we know at least it was a 6 or a -6. That's where this property is coming in. Now that never happens for odd powers. So if we have the cube root of -3 cubed, right? Here if we cube a -3, you get -27. And the cube root of -27 would still be negative. The principal would have the same sign as the original, so that would give you -3. So it's just saying in this case, you can just drop the odd root and the odd power and just put the argument in here, right? Just put u. But if it's evens canceling out, you're going to have to put the absolute value. That's why that's going to pop up. we'll look at it as it arises, but it's not anything to get super worried about, and probably not anything I would even take off for a whole lot. Does that make sense there? So here are a few examples of how we can use those properties to help simplify radicals. In general, when you have a radical, again, it could be a square root, a third root, a fourth root, whatever, we want to get as much stuff outside of the radical as we can. Okay, now I don't want you to type it in the calculator. None of this today you should be using a calculator. It's just practice on manipulating these. So what we'll do here is we have the fourth root, right? We see the index number of 4, remember, sitting in the radical sign. So the fourth root of 80. So first we want to ask ourselves, well, do we know any number that if you take the fourth power, you get 80? We don't, right? That's not really a thing. But what I might do here, if you haven't worked with them in a while, is we're working with a fourth root. It's just helpful to kind of think about or to write out your fourth powers. Now, obviously, 1 to the fourth power is just 1. It's kind of a boring one. But 2 to the fourth power is 16. 3 to the fourth power, let's see, that's like 9 times 9 is 81. I can stop looking because 81 is bigger than 80. So it's not going to happen there. But the question is, does 16 go into 80? It does. Yeah, 5 times 16 is 80. So let's rewrite this then. I'm going to use an arrow there. It's not really equal. We're just simplifying here. So we could say the fourth root of 16 times the fourth root of 5. Right? So we're taking advantage that this is a product of 16 and 5. And then we're taking advantage that we can split it into 2 different radicals. Okay? And then we know that the fourth root of 16 is the number 2. So the answer here would be 2 times the fourth root of 5. As you're doing those, an excellent way to check this would be to type this into your calculator. Type this into your calculator. Make sure you get the same decimal for both of those. And again, if you get hold of a TI here soon, start trying to use that as much as we can in class. It'll really pay off for us. Does that seem like a familiar thing to do there? Okay, next up is the square root of 18x to the 5th. So because there is no index number, we know it's a square root. So when I think about our perfect squares, 18 is not one of them, but we know 9 is. So here we can say that this is the square root of 9 times the square root of 2. Right, that'll work for our 18. And then here we have x to the 5th power. Well, if I had the square root of x to the 4th, that would be pretty good, right? Because then I would just get x squared. So let's split it like that. Let's say the square root of x to the 4th times the square root of x. Now as we look here, we're going to get, this is going to become 3. That's going to remain the square root of 2. This will become x squared. Now question, do I need to put an absolute value around it? Well, let's answer that at the very end. It'll be an easy way to answer it. And then here's the square root of x, which is just, x. So with this one, we're going to get 3x squared times the square root of 2x. Here, we're not going to need the absolute value because what would happen here is here we had a 5th power. So if it was negative, it would still be negative out here. It would be preserved, right? If it doesn't really, if this, that it's going to be negative, this would become positive for sure because it's already an x squared, so you don't have to really worry ourselves about that. But you can usually look at the answers. If x is still being squared, you're fine. You don't need it. Does that look okay, that process? Again, don't worry too much about that absolute value part. Here, C is kind of straightforward, right? We have a fourth root of x to the 4th and a fourth root of y to the 4th. So if you needed to, you could split them. The fourth root of x to the 4th, the fourth root of y to the 4th. Now here, if you're taking the fourth root of x to the 4th, that is a case where it's going to cancel out, correct? So we don't know. Back here, if x was negative, we would have no idea, correct? Because we took a 4th power of it. So here we would been preserved. That's why we did not need the square root of the absolute value. So here, we would actually say the absolute value of x times y would be our best answer. It's going to be, the answer is going to be that positive number, but we really don't know if x or y themselves were positive or negative to start with. And as I said, if the absolute values don't get caught up on that, mostly get caught up on the same answer, as you're working through the practice problems tonight, just kind of notice when they show up. I put the whole solution. I scanned the solution manual for the whole section, so should have some pretty good drawn out things for you there. Okay. And then for the last one here, we have a cube root of negative 24y to the 7th. So already I know that 3 goes into 7 2 times, right? So I'm probably going to break up like a y to the 6th times y thing. I want to know that if there's any perfect cubes or third powers that go into 24, well, 2 cubed is 8. I know that 8 goes into 24, right? 3 cubed is 27, which is bigger than 24, so that's not going to help us any. We know that we're able to take, that if we cube a negative number, it remains negative, or if we take the cube root of a negative number, we're going to get a negative answer. So from here, let's split this up as the cube root of negative 8 times the cube root of 3. Okay, we'll just deal with the negative over there. It's nice to get it outside if we can. And then the cube root of y to the 6th times the cube root of y. Right, again, because we like 6 and 3 are comparable there. So here, we know the cube root of negative 8 is negative 2. And then this is going to become y squared, correct? On the outside. So we're going to get negative 2y squared times the cube root of 3y. That's how that would look. Is that working for us there?